Okay, good day. For this video, we're going to solve some problems related to oscillations or vibratory motion. So to start off, let's have example number 1. A 7-kilogram object is hung from the bottom end of a vertical spring fastened to an overhead beam. The object is set into a vertical oscillation having a period of 2.6 seconds. Find the force constant of the spring. So for this problem, we have our given. So we have here our mass, and we have here your spring. So we're given our period, 2.6 seconds. So again, period is the time it would take to complete one cycle. Okay, so we're given the mass at 7 kilograms. Okay, so for our solution or for our required, we want to solve for the value of K or our force constant. So for our solution, this would simply be using our T and the relationship of M and K. So for this, we'll know that the period of a spring is equal to 2 pi square root of M over K. So we have your period, we have your M, so the only unknown is K, so we could solve this by direct substitution. So with this, we'll have 2.6 seconds is equal to 2 pi times the square root of 7 kilogram over K, where K now is equal to 40.88 Newton meter. Okay. So we have our next problem. So a 0.5 kilogram object attached to a spring with a force constant of 8 Newton per meter vibrates in simple harmonic motion with an amplitude of 10 centimeters. Calculate the maximum value of the speed, the acceleration, and the acceleration when the object is at positive 6 centimeters from the equilibrium position, and the total energy possessed by the object. So for our solution, or before we solve, let's summarize our given. So we have here a horizontal spring with mass attached 0.5 kilograms, K is given at 8 Newton per meter. So we're also given an amplitude of 10 centimeters. So for this, for our solution, for letter A, we have our equation for the maximum speed as Vmax is equal to omega times the square root of a squared minus x squared. And as we have said, the maximum speed is experienced when we are at the equilibrium position. So meaning x now is equal to 0. So substituting our values, we have, so before that, we have to solve first for our omega. So omega now is equal to the square root of K over M. We're given K, we're given M. So omega is equal to 8 over 0.5 square root, and it will give us a value of 4 seconds raised to 1, or that's 4 per seconds, or 4 cycles per, or 4 radians per second. Okay, so this one is the same as 4 radians per second. So let's substitute now our values for omega and for our amplitude and x. So Vmax now is simply omega times A. So Vmax is equal to 4 per second, or 4 rods per second times 10 centimeters. Or Vmax is equal to 40 centimeters per second, or 0.4 meters per second. So this is our velocity or speed of the object at the equilibrium position. Okay? So we move to letter B, our maximum acceleration. So for our maximum acceleration, as we have said, maximum acceleration now happens when our object is at the amplitude. And our equation for acceleration, general equation for acceleration is A is equal to omega squared times x. Okay? So we have computed already for omega. Omega is equal to 4 radians per second. So if we are now at our amplitude, so therefore x here is equal to the amplitude. So substituting now the value of omega for seconds, or 4 radians per second, and our amplitude 10. So the acceleration maximum now is equal to negative 4 per second squared times plus or minus 10 centimeters. Or our maximum acceleration now is positive or negative 160 centimeters per second squared, or that's the same as positive or negative 1.6 meters per second squared. So the positive negative sign here indicates that our object is moving either to the left or to the right. So paano yun? So again, if this is our spring, for example, this is your equilibrium position. We have here your positive A amplitude. This one is the negative amplitude. So meaning, at this point, the acceleration is positive 1.6 meters per second squared, while at this point, at this point, the acceleration is negative 1.6 meters per second squared. Okay, let's move to the next question. So what is the speed when the object is at a displacement of positive 6 centimeters from the equilibrium position? So for this, we'll just be using our general equation of the speed, or our instantaneous speed at any point. So when the object is at a displacement 6 meters per, or 6 centimeters, so this one is our x value. So we have our equation, v is equal to omega square root of a squared minus x squared. So you just substitute the values of omega 4 per seconds, amplitude is 10, and x is 6. So we'll be arriving at the instantaneous velocity at 6 centimeters from EP is 32 centimeters per second, or that's 0.32 meters per second. Okay, so for the next question, letter D, the acceleration when our object is still at 6 centimeters. So still, this is the value of x. So equation for acceleration instantaneous is equal to omega squared times x, and that's a negative value. So we'll have now the acceleration is negative times 4 per second squared times 6 centimeters, or our acceleration now is negative 96 centimeters per second squared, or that's the same as 0.96 meters per second squared. So what does the negative sign indicates? It means that it is moving back to the EP from a positive direction or from a positive displacement. Okay? So that's for letter D. So let's move to letter E. Last question, what is the total energy possessed by the object? So again, for the total energy, that is now equal to 1/2 Ka squared. This is when we are at the amplitude. So that will now be 1/2 8 Newton per meter times 0.1 meter squared, or we get a value of 0.04 joules. So if we're going to check total energy, so at any point, okay, so we have 1/2 0.5 kg 32 meters per second squared, and this is our Vmax, or this is our velocity at 6 centimeters. Okay, so we have 1/2 8 Newton meter times 0.06 squared will also give us 0.04 joule. And then we have our total energy when we are at the equilibrium position. So that's 1/2 0.5 times 0.4 meters per second squared, which will also give us 0.04 joules. So as you can see, at any point in our vibration, the total energy is constant. Okay? So that's for number 2. Okay, let's move to the next example. So we have the position of a particle is given by the expression x of t, or x as a function of t is equal to 4 cosine of 3 pi times t, wherein x is in meters and t is in seconds. Determine the frequency, the period of the motion, the amplitude, and the position of the particle at time equal to 0.25 seconds. So for our solution, or for our given, we are only given the equation x of t is equal to 4 cosine 3 pi theta, or 3 pi times t. So basically, our solution will lie on this equation. So for letter A, for the frequency, so we're given our general equation, x is equal to a cosine of omega times t. So for letter A, the frequency now can be taken from the value of omega, which is now 3 pi. And we know that omega is equal to 2 pi f. So substituting 2 pi f equal to 3 pi. So pi cancels out. So we'll have our frequency as equal now to 3 divided by 2, or that's 1.5 hertz. So hertz is the same as 1.5 cycles per second, or that's simply 1.5 per seconds. Okay, so next we have the period of the motion. So as we have said, frequency and period are just their reciprocals. So for the period, that would simply be 1 divided by f, or that is now t equal to 1 over 1.5 per seconds, or the period is equal to 0.666 seconds, or this is the same as seconds per cycle. Okay, next let's move to letter C, the amplitude of the motion. So for the amplitude, we'll just look on to our equation. So we have here A, which is the amplitude. So basically, ang kapareho niya, okay, A here is also this one. So our amplitude is simply 4 meters. Okay, so next we have letter D. What is the position of the particle at t equal to 0.25 seconds? So in here, we'll just simply substitute the time in our given equation. So that will now be equal to the displacement or the position at 25 or 0.25 seconds is equal to 4 cosine of 3 pi times 0.25, or that's equal now to negative 2.8284 meters. So please do take note that if you're going to substitute values and compute for our different values in our equations, you should always be in. So next problem, we have a simple pendulum having a mass of 0.25 kilograms and a length of 1 meter. It is displaced through an angle of 15 degrees and then released to experience vibratory motion. So using now the analysis model for particles in simple harmonic motion, we are to find the period of vibration, the maximum speed, the maximum angular acceleration, and the maximum restoring force of the pendulum bob. So for this problem, for our given, we are given a pendulum, okay, with length of 1 meter. We're also given the mass of 0.25. So this pendulum now, from its equilibrium position, is given an angle of theta, which is 15 degrees. So this is our arc of swing. So ito yung arc natin. Okay? So we'll have here our amplitude. Okay? So this one is also your L. So basically, when we are going to analyze, we'll assume since that this is also our arc of swing. Okay? So given now these values, we can now solve for our first unknown, the period of vibration. So for simple pendulums, we have a direct solution of the pendulum, which is now t is equal to 2 pi times the square root of L over G. So we're given L. Since we are on Earth, it's not indicated where the location is. So this will now be 9.81 meters per second squared. Please do not include the negative sign here, okay? So the G now will differentiate when we have a different location. Okay? So with that, substitute the values. So we'll have 2 pi times the square root of 1 meter divided by 9.8 meters per second squared. So that will now give us a value of 2.0071 seconds. Okay? So for the next item, the maximum speed of the bulb. So since we're talking about simple pendulums, okay, so we are going to consider our arc of swing, which is 15 degrees. So if we're going to consider this, it is very small when it is in radians. It means if we're going to compute for sine of 15, it is almost equal to radians, the radians value of 15. Okay, so if you're going to compute sine 15, it's 0.25, and then the radians value of 15 is 0.26. So they're almost equal to each other. So meaning our simple pendulum is really under simple harmonic motion. So in that regards, we can now compute for the maximum velocity as omega times a. So again, saan nanggaling yung omega? A. This one came now from omega square root of a squared minus x squared. So again, Vmax happen at the equilibrium position. So x is 0, kaya naging omega a. So in that regards, Vmax now is equal to, solve this is we have to solve first for the angular frequency kasi hindi pa natin na-solve kanina. So for the angular frequency, that will simply be equal to 2 pi f. So we have solved for the period kanina. So 2 pi times the period 1 over 2.0071 seconds, the reciprocal of the period. So it will now give us a value of 3.1305 radians per second. Okay, so we have our angular frequency already, but we do not know the amplitude yet. So for the amplitude, we'll now solve this using our angular motion. So theta is equal to A over L. Since we're solving for the amplitude, it can be written as L times theta. So remember, theta here is in radians. So amplitude now is equal to 1 meter times 0.2618, or the amplitude is equal to 0.2618 meters. So we have now our values, omega and amplitude. We can now solve for our Vmax. So Vmax is equal now to 3.1305 per seconds times 0.2618 meters, giving us a value of 0.8196 meters. Okay, that's for your maximum speed. So let's move to the next question, the maximum angular acceleration. So for the maximum angular acceleration, we have solved already for our omega, angular frequency, and our amplitude. So we know that angular or maximum acceleration now, Amax, is equal to negative omega squared times the amplitude. So for this one, we'll just substitute our value. So we have 3.1305 squared times 0.2618 meters, or the acceleration now is equal to 2.5656 meters per seconds. Okay? So basically, the acceleration will still be either a positive or negative value since we are moving backwards and forward to our equilibrium position. Okay? So next is the maximum restoring force on the pendulum bob. So with this, we're going to use now our equation for RF or FR, and we'll be applying second law of Newton's, so M times A, or that's now 0.25 kilograms times 2.5656. So the max, since we're talking about maximum force, so we'll be using here our A max. So with this, our maximum restoring force now will be equal to 0.6414 newtons. So this is the force required to return to our equilibrium position. So, okay. So that's it for our sample problems. Thank you for listening. So if you want more examples later on for oscillations, there are several problems that you can find in our modules. So it has already been sent to you already. So again, thank you, and we'll see you again on the next modules.